Well, great. Thank you so much for that intro and for the invitation to present here. So I'm going to talk today about the second half of that intro, which is looking at stream flow impermanence and talking about the work that my team, large group at USGS and elsewhere, has been working on. And to start off, I will acknowledge this large group. As I've gotten older, I do appreciate these slides because it underscores just there's lots of folks who are part of this project. Roy Sando is a key modeler on this project at USGS. He's in Montana, and there's a long list of folks at USGS. This is also collaborative work with the U.S. Forest Service, with the Northwest Research Station down in Corvallis, and then also some academic partners, notably Kendra Kaiser, who's research faculty at Boise State University. Okay, so I will first start with some definitions. And first off, what is perennial and non-perennial classification and why it is important? And I'll begin with this definition from Bush et al. 2020 of what is non-perennial. It's any loadic freshwater system that periodically ceases to flow or is dry at some point in time and or space. And then, so this fits under the broader umbrella of stream flow permanence, which is this kind of concept of timing, duration, frequency, and extent of surface water presence. And so, these networks can expand and contract over different time scales, and at a given location. This is a picture where one year you have flow and another year you don't have flow. For today, I'm just focusing on the classifying of non-perennial. And the key phrase is at some point in time or space. So we are not looking at, or the models we've developed are looking at the probability of year-round flow. We're not talking about for how long that flow is occurring. We're not talking about how many times that occurs. It's just kind of a probability of membership of these classes of either perennial year-round flow or non-perennial. At some point it's going to go dry. And accurate classification is important because one, non-perennial streams are globally abundant. And they account for the majority of the channel network length. So this is a picture of CONUS, contiguous US, with the mapped perennial streams, and then overlaid the mapped non-perennial streams. And you can see that overwhelmingly non-perennial streams account for the majority of the channel network. And we also know that mapping of these streams, despite our best efforts, can be inaccurate. So Hafen et al. In 2020 did, among other things, an analysis where they looked at comparisons of the classification by the National Hydrography Data Set of perennial or non-perennial compared to field observations. And these field observations were just in the Pacific Northwest. And this is how the agreements and disagreements work out. So agreements would be that if you had a wet observation, it was it agreed with the perennial classification. A disagreement would be if it was dry and you had a perennial classification. So along the x-axis, you have stream order. So the lowest stream orders, 1 and 2, those are our headwater streams that extend the highest up in the headwaters, up on the hill slope. This is just a distribution. And you can see that in the first and second order streams, we have way more disagreements compared to the other. As we move down the river network into these higher order streams, we generally have those observations working out. So we're getting it half wrong, especially in these headwater systems. And this has regulatory implications. So generally, perennial streams have more protections. They're generally protected or have stronger protections and regulation under the waters of the U.S. So that's WOTUS and the Clean Water Act, which is CWA. And then also just on a state and local level, there are different regulations are managed. These streams are managed differently if they're perennial or non-perennial. So perennial streams in timber harvest lands are going to have a vegetation buffer around them, where you have here, this is there we go. You have a clear cut here, and then these green strips here are the vegetated buffer widths that need to remain and are not cut. As well, like from year to year, annual grazing permits will depend on whether there's water availability on the landscape. So this figure here is the upper Missouri Basin. So this is most of Montana and the eastern half of the Dakotas. And the overlay is grazing allotments. And so permits will change depending on if they have water availability on that landscape. So this is useful. It pays and would be useful to understand accurate classification. And then just from a basic science perspective, there's biogeochemical processes that are distinct between these two systems, and there's like a complex gradient, of course. This picture, Delvicchia et al. In 2022 is a conceptual figure that has these hypothesized concentrations during periods of flow connection and disconnection. And so the blue lines or the blue colors shading corresponds to where there are hydrologic connections, and the red is where there's disconnections, and you have different gradients or different rates. You have different relative concentrations depending on if things are dry or wet, and it also will then change in time. And again, this is hypothesized. This is all stuff that they're still trying to figure out. And as well, there's all kinds of critters that I don't know anything about, and but they also live and dwell in these systems. So again, accurate classification of perennial and non-perennial allows us to scale up information at this level and at this smaller watershed scale up to these larger landscape extents in order to draw some larger conclusions. And so my research objective, or our research objective, is can we provide estimates on the probability of year-round flow that improves on the spatial and temporal accuracy of existing models? And when I say existing models, I'm talking about the NHD, like perennial and non-perennial classification, which is a static classification. And really what we wanted to do was capture, can we account for this year-to-year variability? And so a key challenge was what data to use. We know there is data scarcity of stream flow in these headwater systems. There's a bias of strain gauges to the perennial network, to the downstream network. And there's a limitation in data in these small headwater streams, which is where like most of this perennial, non-perennial activity occurs. And so our solution was to leverage existing data of these simple flow, no flow observations. So these are common in many field surveys. These are just simple data that you're able to achieve at a greater spatial scale. So we aggregated a data set from 11 different agencies, federal, state, tribal, local agencies, and was able to gather about 24,000 observations, snapped them to a hydrography, and then a subset of those we used in to use in our model for the Pacific Northwest, and they were categorized as wet or dry. In order to be wet, that observation had to occur during late summertime flow. So, and these are just kind of one-time observations. This is not time series data. So if it was dry, if it was a dry observation, it can occur any time of the year. Most of the time, it occurred during the late summer. That's when these data collection efforts mostly occur. But in order for it to be wet, it had to occur like after July 15th up to like September 15th. And then our modeling approach was a random forest classification. This is pretty robust to having what I call kind of a kitchen sink approach, where you can add in a lot of different covariates, which allows for not really a good mechanistic understanding, but good estimates and higher accuracies. We used a suite of physiographic variables. This is all gridded data that we, these gridded data sets. So we use topography, land cover, soils, permeability, and base flow index. And then we also use climatic variables that were either processed as annual or monthly data or time steps. And then we process them as flow conditioned continuous parameter grids. So these are essentially just basin average values as you march down the watershed or down the stream. So with the reasoning that stream flow and stream flow permanence is an aggregation of the basin scale conditions, that's why we process these so that you're not having just the local data or just the local value as your predictor variable. And then this is the product. This is what our model on general is. It provides annual probability of year-round flow for each year under the specified modeling domain. So it doesn't predict forward. And it's essentially kind of like a hindcast where you have given it the climate data for that year, and it provides an estimate of the probability of year-round flow. So the spatial domain was the HUC 17, the hydrologic unit code, 17 Pacific Northwest region. So it's all of Washington, most of Oregon, most of Idaho, a little bit of Western Montana. And it's raster data. It's at a 30-meter resolution. So when you zoom in, this is what that data look like. And how it's symbolized is you have the values scale from 0 to 100, with those warmer colors of red, lower probabilities of year-round flow. Cooler colors are higher probabilities of year-round flow. And we use in order to classify this into, non-perennial or perennial, we use a threshold of 50%. So as you increase distance from that 50% threshold, you have, potentially more certainty about that probability. And like stuff that's hovering around 50% may represent streams that may be on the edge, like they're kind of perennial in some years, or they're kind of intermittent. They're just kind of those threshold streams. Or it could just be a limitation in the model where what's controlling stream flow permanence at that location is not well captured in the model. Okay, and then just some details about the model. So just like some housekeeping about the random forest. We set the number of decision trees to 500, and that each have a subset of variables that are used to split the trees into these nodes or branches that class a point as wet or dry. And the number of predictor variables are randomly selected to split the data at each node, and that was set to 5. And we used out-of-bag error to evaluate accuracy. So this is just kind of a standard metric to evaluate models. And that the out-of-bag area was approximately 20%. So these models, the global model was approximately 80% accuracy. And then the top 4 most important variables were total precipitation, mean daily minimum temperature, % forest cover, and base flow index. So sorry, this is a variable importance figure where all of the variables used in the model are ranked in terms of order of importance, with the top being that are the variables at the top are the most important. Yes, so precip and temperature were the most important, followed by % forest and base flow. And I just wanted to demonstrate or illustrate what this model kind of looks like in terms of like capturing or at least modeling that interannual variability. And so this is a nice quote from Ken Fritz, who's at the EPA and is, has done a lot of work in these types of systems looking at stream flow permanence. And it's kind of small, so I'll just read it here. Rather than having distinct rigid boundaries, stream reach is classified as perennial, intermittent, and ephemeral may more accurately be described as dynamic zones with stream networks. And so I think how this is coded right now, or how we've symbolized this, is, again, you've got this probability that extends from either 0 to 100%, or in this case, 0 to 1. All the blue lines are the probabilities that are 0.6 or higher. All the red are 0.4 and less, and then things that don't have a color, the flow lines that don't have a color, have those values of 0.4, between 0.4 and 0.6. So this is the estimates for 2008. And then in 2015, which is the great snow drought of in the Western US, where we didn't get very much snow, we got the same amount of precipitation, it just came as rain. And you see an expansion of those streams that are estimated to have lower probabilities of year-round flow. These are the streams that are expected to have gone dry that year, and a contraction of those areas that might be more reliably counted as perennial. And so we just have estimates for each year, but these are two nice contrasting years for the Boise River basin. Okay. And at that point, so this, that came out in 2019. We started that project in 2016. And at the time, these types of type of streamflow permanence prediction had not been modeled at that resolution and at that geographic extent. So we've extended on this kind of modeling framework. We've developed another regional model. And sorry, I didn't introduce it. The model is called PROSPER. It's the probability of streamflow permanence. So it's the PROSPER model. The Pacific Northwest is PROSPER Pacific Northwest, and then PROSPER Upper Missouri. Side note, we first were going to call it the HIP tool for headwaters intermittency prediction, but that didn't stick. So we went with PROSPER. So the USGS really likes acronyms. Okay, but that's just a side note. So we've got these regional models that extend into the Upper Missouri. So this is what that area looks like in terms of wet-dry observations and the density of that data. And so that just came out in 2022. And then we have sub-regional models for within the Pacific Northwest region. So specifically, we've got Mount Rainier and then Western Oregon. And these were areas where we wanted to take a second look, where we knew PROSPER really was not doing very well, or we didn't have much confidence in those predictions, largely because there was an absence of data. And that's shown here in this figure. These hatched marks are these zones that we noted in our 2019 paper, where we know we know that these were areas that were not well represented by the model. And so they all have the same modeling approach, the same random forests, the gridded flow conditioned covariates, these wet-dry observations. Some differences are with this Upper Missouri model, we have a higher resolution prediction grid. So this is a 10 meter. We provide predictions on 10 meters instead of 30 meters. We at no means are we in, that provides an estimate, but we're not in any way saying, there is flow or not flow at this 10 meters or at this 30 meters. But it's a way of looking how we like to look at the data or interpret the data is if you're seeing kind of general trends that can provide some information about what's the flow dynamics or the stream flow permanence dynamics at that system. But we are not, providing you kind of look at the forest and not exactly at a specific tree when you're looking at these types of data. And then some other things I want to highlight about the Upper Missouri is that it provides forecasted, short-term forecasted annual predictions. So I said that these models don't predict well into the future. But what this model will do is it'll take all the climate data that's available up until June, and it'll provide a prediction for what the annual or what the probability of year-round flow will be. And this is because this project was funded by the Bureau of Land Management for grazing allotments. So they wanted to know in the spring where they can start to do their permits, where can they expect to do water, where can they expect to see and have surface water available. So there's forecasted annual predictions. And then this is for a longer prediction period than the Pacific Northwest. It starts in 1989. And then it also is for years going forward. So as new data come in more new predictions will, as new covariates in the climate data come in, new estimates for that year will be made. And then for the sub-regional, those two models, so this one just came out, and I'll talk about it in a second, for the Mount Rainier. Both are in different hydrographies. So the Mount Rainier one was just kind of wanted to leverage what the Pacific Northwest had. So we used the same relatively coarse grid layer of, or stream grid layer of 30 meters, but Western Oregon is actually at 5 meters. And then what we're finding is that these sub-regional models have generally a lower accuracy than the global, these larger regional models, which hover around 82%. Mount Rainier is about a 74% accuracy, and we're still figuring out what Western Oregon is, but it's also in the 70s. And despite that, though, I do think that these are improvements, and I'll get to that in a second, but I will describe this model a little bit. This is the Mount Rainier model that we just developed, and the model accuracy is 74%. Notably, these climatic variables, climatic variables were not top predictors. So you can see the most important variables were drainage area, geology, topography, land cover. These are static variables that describe the landscape and are not changing year to year. And we think this is a scaling issue. I mean, this was a very small area. The climate data, excuse me, is at a larger grid area. And this was also over a data set, a time period of data collection of only 3 years. So we just didn't have the variability of those climate variables. That's not to say at all that, the hydroclimatic conditions for a given year are not super important or influential for streamflow permanence in this landscape. But interestingly, what we found is that approximately half of the stream reaches, about 49% of the stream reaches, have probabilities of less than 0.5. So there's lots of streamflow impermanence, or expected streamflow impermanence in this system. And you can see the coloration here kind of demonstrates that. You've got these oh, this is a little skewed, but you've got these blue colors. This is where the glacier is, and the streams, the stream grid is overmapped. So the streams extend a little bit higher than what's reality. But you can see these dark blue, these are the streams lines with high probability estimates. And then, these surrounding areas that are in lower elevation and not draining the glaciers, those are, these are the areas in the streams that are going dry, which I found interesting and surprising, given that this is a maritime wet climate of Mount Rainier. But streamflow impermanence was more than I had expected in this model. But I wanted to make the point that despite the lower accuracy of 70%, I do think this local model provides better estimates of permanence class compared to that regional, to our regional PROSPER model. And this is evident by the distinct separation of probability estimates for the observations that were used in the model. So to the left is a distribution of the Mount Rainier random forest model of estimates for dry observations in pink and wet observations in blue. And you can see there's kind of a separation where, those probabilities, those distributions are different, whereas the PROSPER model was not able to differentiate that. So, PROSPER just doesn't work for the regional model. PROSPER just doesn't work for this system, in part because of a lack of data. There is pretty much no data. This is all new data that was collected for this particular local project. And we also incorporated local variables, like specifically geology, which was the second most important variable that was at a resolution that was not possible to apply at these larger regional extents. And so then talking about where you can find PROSPER, we are the USGS. So we provide information. So these are all in data releases and science-based, but they're also the models, you can see output in stream stats. if you're familiar with that. So you just go to stream stats, so you can click down to Prosper, and then you can see it's kind of colored here. You can see kind of the coloration in the Pacific Northwest region, and you zoom into a location and it'll provide a probability. This is very coarse. We're hoping to make this snappier looking, but it'll just report the probabilities, and it translates it also to a flow class for each year. And then we've since, expanded on that with these subsequent models with hopefully improved visualization. So the Prosper Upper Missouri has a map viewer. That's all, that you can go to, and it provides annual estimates. It provides a summary and trend statistics of the probabilities. It provides climate overlays, so you can look at like, oh, things are looking really dry this year. What's going on? You're like, oh, well, the precipitation was really low. So these are just kind of ways that folks can start to look at the data. And then for this Western Oregon project, which we partnered with Forest Service with, we also have a visualization that we're developing that is in review now, that provides the summary of this classification status, and it also provides some statistics on how it compares with that F code, or that classification of perennial and non-perennial. Okay, and so a couple points I wanted to make about these models. I wanted to return to this idea of using simple wet-dry observations, because it is extremely convenient and it is very useful. These conventional stream gauges, this is a picture house for USGS. It provides, we all love this data, it provides high quality time series data, but we know there's a bias to perennial systems. And it's also can be prohibitively costly. I mean, in Washington State, a USGS gauge is about $30,000 to install and operate a year. And that is usually, that cost is shared by a local partner that is interested in that data. So this data is beautiful, but it's limited in its location. And then here you have these flow, no flow observations, which is kind of this like buckshot geographic approach where you have very simple data at greater representation of these headwaters and non-perennial systems. So this is not exactly a silver bullet, but I continue to be surprised at how useful these data can be once you've processed them and cleaned them up, and worked with them for a bit. And with that, there's quite a bit of momentum for these data collection apps. And so, USGS and Forest Service has what we call FLOPER, Flow Permanence Mobilization App. So that's over here on the left. There's other crowdsourcing mobile apps that are out there, Stream Tracker, which came out of Colorado State, Crowdwater and Driver, which are both in Europe. And they're just essentially very simplistic, like you just have your phone and you have a geographic location, you map it and you take a picture of that field location, and you have a note of whether there was flow or no flow. These are all just generally, there's different questions depending on your on which survey you're using, but it all generally comes down to it's a date, it's a location, and it's a flow, no flow. One note with us for FLOPER, we developed this. It's not necessarily this. These other three are just essentially like citizen science. Like anybody can go and use it and download it and access it and start collecting data. FLOPER was, we were wanting to initially keep to folks who are essentially in agencies who are already collecting data, or universities where they're already out in the field collecting kind of field data, and also had access to a high accuracy GPS. This was developed first for Western Oregon in these rugged forested canopied streams where you can lose precision and our points like end up on like a hill slope or between a tributary and the main stem, and you're like, what is going on here? I don't know how to process this data. So it's a little bit different. But just to show, you know, how what our data are looking like, we launched in 2019. We have, you know, since that time, we have about 20,800 observations. It's mostly in the Pacific Northwest. This is our dashboard that we use to look at the data and view it. You can see what are the different kinds of flow classes. You can see that there's no data, there's black spots. That means that the person's collecting data wrong. So you can call that organization and say, okay, if you're in the field, there should be no data, like you're in the field. So I mean, there's something going on with that survey, and we need to help them, you know, make the correct selections. And you can also click on a point and it'll show you a picture, and it'll show all the information that's associated with that observation point. And so then one point here, and I'll return to it a little bit later, is again, this is not a silver bullet. This is pretty fraught. You know, you can, I'm not sure if many folks have like dealt with crowdsourced data, but it's pretty easy to collect information, and about half of it ends up actually being useful, because even with very simple protocols, there's just a lot of room for error. So our motto here is, if we can get a lot of data over a lot of years, some of it's going to be useful. And then, so just kind of real quickly, the next couple sections of the talk is, I wanted to talk about, you know, some of the applications of these Prosper type models. And essentially it all just boils down to, I mean, it's all spatial gridded data. So how can we, you know, integrate and overlay them, do some statistics to come up with some sort of higher understanding of something. In my sounds cynical, but that's it is exciting. So an example of this is a collaboration we have with Virginia Tech. This is funded by the USGS Northwest Climate Adaptation Science Center, where there's a couple different components of this project, but here this slide is just talking about developing a rarity and climate sensitivity index. So it's taking you know, we've got our modeling domain that has that has our flow lines. All of these points are presence absence records for non-salmonid fish species. And then this is building on work that Meryl Mims, who came out of SAFS, had done while she was doing her postdoc with USGS, where she developed a rarity and climate sensitivity index, where she took observations and gridded data sets to develop an area of occupancy. Oh goodness. Area of occupancy and climate sensitivity. So here she would take prism data, air temperature and precipitation, and plot these species based off of these two axes. So for a given species that, you know, has a large area of occupancy but low climate sensitivity, these are these. Low sensitivities. These are going to be our less rare and sensitive species. Conversely, small area of occupancy, high sensitivity. These are our rare and sensitive species. And then you can rank them. So she had done this just with the gridded climate data, and then we're extending it by just overlaying Norwest water temperature data and the Prosper data. Another example of how, you know, these models can be used is adding it or integrating it with other data sets that can describe water presence or surface water presence. So this is work with Roy Sando. I'm not part of this project. They call it SWIPE. Sorry, I find hilarious. Surface water index of permanence, where really they're just combining probability of stream flow permanence for the Upper Missouri model. They're taking Landsat data and looking at surface water extent and how is that changing from year to year, doing some fancy footwork, and they're coming up with an index of a surface water index of permanence. And this can be useful to track for the upper Missouri Basin. There's lots of reservoirs. This is prairie pothole landscape, and it's pretty dry. And so knowing the year-to-year combined information of reservoirs, water, these water bodies, and streams can be useful. And then so some next steps for what we are doing to like expand our models and also improve with what we have. I mentioned that, these data can be these wet, dry observations, especially when they're collected by all kinds of folks. It can be hard to post-process, to be like, where is this? This is not, to try to figure out where to ascribe that location, because we have to ascribe all of those points to a hydrography. So we're developing tools for automatically processing thousands of new flow and no flow data, and then providing crosswalks among hydrographies. So I'm not sure if you all work with different hydrographies, but the National Hydrography Dataset has a medium resolution, a 30-meter resolution. This is coarse. We have a high resolution, which does a better job at capturing the headwater regions. And then there's also various other, people have their own hydrographies of interest, and they don't necessarily perfectly align. So you need to develop ways to crosswalk. But just to illustrate some of the mundane issues that we have to deal with, where you have, this is a figure here where you've got our original flipper point. This is the red triangle. You can automatically snap it to a flow line, but then you have to reassess, is that a proper snap? And so confluences become a big issue, where this got snapped to this large main stem, but really it needed to get manually moved and assessed to get moved to a smaller tributary. And then you also have something like this question where I was talking about, where you've not good GPS location. And so you've got literally the point is on a ridge line between two steep ravines, and you need to ascribe that location. So it may snap it to this location, but then you look, there's already a point there. So moving it out here. There's all kinds of ways and codes and stuff that script lines to kind of do these QA/QC checks. So we're just trying to kind of get that a little bit more robust, and because it matters when you are moving these points when the drainage areas are so small. So if you move it wrong, it has almost disproportional influences on, on how accurate your model is going to be, because drainage areas is often a key predictor. And so moving it down or up just a little bit can have big effects. We're also developing guidelines for how end users, folks like Bureau of Land Management, Forest Service, and other agencies that are having to make water resource decisions, guidelines and kind of ways to reconcile these different data sources. So there's the F code with perennial, non-perennial classification. There's this probability. What do we do? What do I do with the probability of 0.6? So we're rerunning the model to develop the standard errors associated with each probability. And then we're also creating visualizations so that we can provide all of this information at one location, so that an end user can can take a look and be like, okay, where are things agreeing? Where are things not agreeing? And that can help provide context for subsequent decisions, like, do they need to go out into the field and do a collection of data, make an observation, or is there enough evidence for them to make a call of yes, this is perennial, or no, this is not perennial, and then move forward. And then finally, we're in the process of creating an operational model where we have this tool that ingests these new observations. It processes these new covariates for years going forward. It recalibrates the model, and then it provides estimates or new predictions for that newly calibrated model. So this is what we're calling our operational model. And so developing the framework, this would be a kind of a cloud computing process. But developing the framework for this to occur and in both of these regions, the Prosper Pacific Northwest and the Upper Missouri, is what we're trying to achieve. And so thanks for sticking with me. The conclusions here, this is kind of a sweeping kind of display of all of these types of models and what we're trying to do with them. So take homes here is the Prosper models have increased the spatial and temporal resolution of streamflow permanence classification at these regional scales. So currently we still we haven't been able to top this. We still have the NHD and we've got Prosper. And so I'm looking forward and welcome any improvements of what we have here. These flow, no flow observations are very simple and they are unconventional. They're, compared to, what we have for stream flow gauges. They're very useful and there's a lot of promise. And I think we just need to figure out how to most efficiently use them, but I'm excited about them. And again, there's also just lots of opportunity for ecological applications with these and other data sets. And with that, I will close. Thank you so much.